So far, we've been dealing with how to compute the derivatives of the form y equals f of x, where y is defined explicitly as a function of x. However, some relationships between variables are expressed implicitly, and we'd like to know how to obtain the derivative in this situation too. For example, the unit circle is described by x squared plus y squared equals 1, which describes an implicit relationship between x and y. Because this curve does not pass the vertical line test, it's in fact impossible to solve for y explicitly as a function of x. The best we can do is solve for y in terms of x above the x-axis, for example, or below the x-axis, thereby obtaining two different functions, each of which we could compute the derivative of separately. It would be better if we could omit this process of solving for the myriad expressions we could get when solving for y of x, and instead just differentiate the implicit equation x squared plus y squared equals 1 directly. Implicit differentiation allows us to do this. Let's demonstrate this technique through the example of the unit circle. The idea is to think of y not just as a variable itself, but rather as a function of x, so that the implicit equation can be thought of as x squared plus the quantity y of x squared equals 1. Upon thinking in this way, then, we can differentiate both sides of this equality with respect to x to obtain a new equality. On the left-hand side, when we differentiate, for the first term we just get 2x, and for the second term we realize that we're going to have to apply chain rule, because there are two functions being applied to x here, first y and then the square function. This outer function is just the squaring function, and so chain rule says that the derivative should be equal to 2 times y of x times y prime of x. On the right-hand side, we're just taking the derivative of a constant function, which means that the derivative is given by 0. What we obtain then is an equation involving the derivative y prime of x. Treating y prime of x as a variable, we could try to isolate it. To do so, we could first subtract 2x from both sides, and then divide by 2 times y of x. What we obtain then is y prime of x equals minus 2x all over 2 times y of x, or minus x over y of x. At this point, it's common to omit the dependence of x from this expression, so we'll often just write y prime equals minus x over y. The geometric implications of this computation are interesting. We've now obtained an expression of the slope at any point along the circle in terms of the variables x and y. In other words, at the point x, y, the slope of the tangent line there is given by the quantity minus x over y. For example, the point 1 over square root of 2, 1 over square root of 2 belongs to the unit circle because this point satisfies the property that the sum of the squares of its components is 1. And at this point, the slope is given by minus x over y, which becomes minus 1 over square root 2 all over 1 over square root 2, which is just minus 1. Geometrically, this seems to make sense, since the tangent line passing through the point 1 over square root 2, 1 over square root 2 is perpendicular to the radius extending to this point, which has slope 1. As another example, consider the point 0, 1, which belongs to the unit circle, as the point on top of the unit circle. The slope there is given by minus x over y, or minus 0 over 1, which is just 0. This makes sense because the circle is flat there. Let's do another example of implicit differentiation. Consider the curve xy plus y squared equals 2. Because when x equals 1 and y equals 1, the equation is true, we know that the point 1, 1 belongs to this curve. Our goal is to find an equation of the tangent line at this point. For such a line, we need the slope, which is given by the derivative. And to find this derivative, we'll use implicit differentiation. So what we'll do is we'll take the derivative of both sides, always thinking of y as a function of x. For the first term, x times y, when we take the derivative, we see that we're going to need to use product rule, which says that the derivative is equal to the derivative of x times y plus x times the derivative of y. The derivative of x is just 1, so this just becomes 1 times y plus x times y prime. For the next term, y squared, we can use chain rule to find a derivative of 2y times y prime. On the right-hand side, the derivative is just 0. So what we're left with is the equation y plus x times y prime plus 2y times y prime equals 0. The quantity we're interested in is y prime, so we'll try to isolate it. First, we'll subtract y from both sides, and then we can factor out a y prime from the left to get y prime times x plus 2y equals minus y. Dividing both sides by x plus 2y shows that y prime is given by minus y over x plus 2y. The slope we're interested in is the one where x and y are both 1, so we make these substitutions to find a slope of minus 1 over 1 plus 2, which is minus 1/3. Once we have this slope, then we can find an equation of the tangent line using the point slope formula. An equation is given by y minus 1 equals minus 1/3 times the quantity x minus 1.